Okay, in this lecture, we'll talk about the electric force, which is a force between electric charges, and we'll talk about what that means. And also do a Newton's second law refresher, something that you saw in the previous semester of physics. So we'll talk about what exactly the electric force is. It's called the Coulomb force, how you do a Newton's second law problem generally, and then we'll do an example, which is a Newton's second law that involves the Coulomb force. So to start out, just an overview of this semester, we'll talk about charges, charges and their interaction together. So here you can see one charge with a force on it due to Q1 and a force due to Q2. And that will lead to the idea of currents and electric field and magnetic fields. And it turns out that those things are actually connected together. And those things will become part of something called the electromagnetic field, or an electromagnetic wave, which, as you can see here, the electric field is pointing like this, and the magnetic field points like this. And that electromagnetic wave is actually, it has a name, it's called light. So there is an overarching principle of this course, which is the interaction of electric and magnetic fields, and that's actually the study of light. But we're going to start out with some simpler ideas, which are just the interaction of electric charges. So the force between two charges is called the Coulomb force. It was introduced back in 1785 by a French physicist named Charles Augustin de Coulomb. And it is a vector, so we need to express what its magnitude is. So the magnitude is this equation here, which tells you that the force between two charges, like Q1 and Q2, here I'm labeling one as a positive charge and one as a negative, it has a magnitude which is proportional to the product of their charges, the absolute value of that, but it's inversely proportional to their separation distance. So the separation distance on the picture here is just this distance here, that's R1, 2. And the direction is given by experiments to be seen as like charges attract and opposite charges repulse each other. So if we go back up here to this example, we have a positive charge and a negative charge. So if I were to draw the force of Q1 on Q2, then that would be an attractive force. So the force would look like this, force Q1 on Q2, like that. The magnitude of that, the length of this vector, would be given by this equation. K is called the Coulomb constant, and it's something like 9 times 10 to the 9th in whatever units would give you back newtons when you use coulombs for the charge here. So let's just do two more examples for these forces. So what if I were to draw the force on Q2 in this case? So the force on Q2 in this case is going to be a repulsive force, so it's going to point directly away from Q1, and we'd write it as the force of Q1 on Q2. And what about the force on Q1 in the second case due to Q2? So the force on Q1, since these are opposite charges, it would be an attractive force, and I can draw that force vector as pointing towards Q2, and that's the force on Q1, the force of Q2 on Q1. Okay, that's the notation that I'll use. So, now that we know what that force is, let's go on to talk a little bit about Newton's second law. Newton's second law, as you remember from last semester, is F is equal to ma, but it's actually, of course, a vector equation. It's the net force on an object is equal to the mass of that object times the acceleration of that object as vectors. So because it's a vector equation, we need to do some sort of special work to try and get information out of that to convert the vector equation into numbers. So let's just go through very quickly how you do that. And I've given you sort of, how many steps here? An 11-step process to do that. So the first thing you do is you draw a picture. So let's just draw something like we might have seen in 230 or in 220. We have an object, a box of mass m on a ramp. And the first step is you draw a picture and you label everything. So I'm going to label the mass there, I did. And then we have an angle, theta, here for the box. And I guess that's enough for now. The second step is you draw a free body diagram. And a free body diagram just means you draw the forces that are acting on that object. And I'm going to draw my free body diagram right on the object. You could put this dot off to the side if you want, but I'll just draw it there. So all the forces are, we have the force of gravity pointing down. We have a normal force because it's in contact with a ramp. And maybe that's it. Maybe those are the only forces that we have. Now, the next thing, I called it step 2b, is to also indicate the acceleration vector. And the reason is because we're going to be using this equation, F net is equal to ma, and the free body diagram is meant to represent this equation graphically. So it's not really enough just to put the F net, just to put the sum of the forces acting on the little dot there, but you also need to show what the acceleration is. So I'm going to assume that the acceleration is parallel to the ramp, and let's just say that it's going to go down the ramp. We'll be able to show that that's true if we were to solve this problem, but for now I'm just going to show that the vector points along the ramp and down. So now my free body diagram is complete. The next step is you write down Newton's second law. So, and you're going to do that for every object. In this case I only have one object here, but if you had multiple objects you would do it for each of them. And when I say write down Newton's second law, I mean write down exactly F net is equal to ma, or you could write sum of the force vectors if you want to with a sigma, so sum of the forces is equal to ma. And then you make it specific to your problem. So what do I mean by that? I mean you look back at your free body diagram and you say, okay, I have two forces inside of F net. So these two forces need to be replacing the expression for F net. So I'm going to write Fn, and they're vectors, so I have to write them as vectors, plus Fg. And then I can just write is equal to ma. So now I have Newton's second law, and it applies to exactly to the picture that I've drawn, to the free body diagram that I've drawn above. Okay, the next step, step 4, is you choose a coordinate system. And that just means that you draw an axis. It tells you how you're going to break up these vectors into different directions. So maybe I'll use red for the coordinate system, and maybe I'll use this as my coordinate axis. So I just draw an arrow in the positive direction and call one side x and one side y, and that's going to be the coordinate system that I use. Okay, now that I've chosen it, now I can deal with my vector equation that I have here. And the way that you deal with a vector equation is that you write out the Newton's second law again. What's true for a vector equation will also be true for a component equation. And so I'm going to write this as fnx plus fgx is equal to max. So basically all that I'm doing here is I'm assuming that each of these vectors is actually a pair of components, ax and ay, and I'm just pulling out the first one to write in this first equation. So I just pull out the x component in each of these three vectors there. And now we start to actually try to calculate things. So we want to express each of these components. This is step 6. I want to express each of these components in terms of the magnitude of that particular vector. So I want to find out what fnx is in terms of the magnitude fn. So let's look at it up here. So maybe I'll redraw my coordinate system quickly. So here's my coordinate system, and I'm going to draw fn on it. Fn. And I can see that there's going to be a component here along the y-axis, but that is going to be actually fnx. So this is the fn vector. This number here is fny. But if I go back to the x-axis, I land at fnx is equal to 0. So the expression of fnx is just 0. so I write it there. Then I go to FG, and I probably should have given myself more space here. So FG points directly down, which on this coordinate system looks like this. And I want to find the x component. So where does it project perpendicularly back to the x-axis? And it's that number there. So this number is FGX. And I want to find out what that number is. And how do I know what it is? Well, I can see, for example, this is actually the ramp angle here, theta. So if that's true, then this is not theta. But since this is 90 degrees, this angle here is theta, and also this angle here is theta. So that tells me I can look at this little coordinate system here, this little triangle here, where I have theta, I have the magnitude of FG on the hypotenuse, and this little side is what I'm looking for. So you can see that x is equal to FG sine theta. But I have to be careful, FGX is this number here, and this number is a negative number on the x-axis. So I replace FGX with minus FG sine theta. Okay? And finally, I need to also do the same thing to the right-hand side of the equation. So I have m times, and let me move this over, ax, so I have to find the x component of the acceleration vector, and you can see that if I were to take this vector and place it on this coordinate system, it would point in the negative x direction, and it would not point at all in the y direction, so the whole thing would just have an x component. So ax, a sub x, the x component, is just minus the magnitude of the acceleration. And we might just rewrite this equation to make it look a little simpler as magnitude FG sine theta is equal to ma by multiplying both sides by -1. So that's how you find the components, and then you repeat this for the other equations. So now I could write out the y equation, fny plus fgy is equal to may, and then do the same thing for that to find its components. And then finally, if you have other objects, you would do exactly the same thing. Draw a free body diagram, write out Newton's second law, look at its component equations, and you'll end up with a number of boxed equations at the end that relate all of the magnitudes. What you can do with those boxed equations then is you can use expressions that you know for the magnitudes of different forces. So for example, I have an Fg here, so that equation could become mg sine theta is equal to ma, or just g sine theta is equal to a. I would have another equation somewhere else, and whatever I need to find, I would find by using these boxed equations, doing some algebra. Maybe I can just use one equation, maybe I have to use multiple equations with multiple unknowns. So that was a lot, but that's the process of doing a Newton's second law problem. And now we can use it to solve a problem in this semester's course. So the example question says we have two identically charged balls, each with a certain mass, and they hang from a light string affixed to the same point on a ceiling. So let's draw that picture here. So we have a ceiling, we have strings hanging down from some point on the ceiling, and then we have identical balls. And I drew it like this because we're told that the strings make an angle of 10 degrees. So the angle here is 10 degrees, but I'm going to do Newton's second law, and I'm only going to focus on one object. So I'm actually going to instead give myself an angle here and call it theta and say that it's 5 degrees. So here's my picture. Have I added everything? I guess I should also include the mass there. And then we're also told that the balls are charged, so there should be a charge on each ball. So I can say there's a mass and there's also a charge on it, and of course the same thing over here, so M and Q over there. So I think I finished that first step. I drew the picture. Now we want to do the next step, which is the free body diagram. So we have to look at all the forces. So some of them are familiar to us from the first semester course. We know that if there's a rope or a string attached to an object, then we have a tension force. So that's one. We know that there is a gravitational force for any object that has mass. So I'll draw that. And then we also have a force which must be holding it to the right there. And that's the Coulomb force. So how do we know that it should be pointing to the right? Well, that's because these two things are identically charged. So you have the same charge that leads to repulsion. So there must be a force, and we saw from that first page that the definition of the force is that it points away from the other ball. So this is the FQQ force, the force of the left charge on the right charge. And that's it for the free body diagram, but remember the free body diagram represents Newton's second law, so we want to also include the acceleration there. And so I'm just going to state here that the acceleration of this object is equal to 0. It's hanging at rest. There's no motion, there's no acceleration there. So now we can do Newton's second law. So we have a free body diagram that represents everything in Newton's second law. I write out Newton's second law. F net is equal to ma. And then I make it specific to this situation. So it's the tension force as a vector plus the gravity force as a vector plus our new Coulomb force as a vector is equal to ma. Next step is I choose a coordinate system. So let's just choose this as our coordinate system, x and y. In fact, let me draw it a little bit bigger because we'll try and find the components on it. So here is our bigger x and y coordinate system. And we write out the same exact equation, but instead of for vectors, we write it for the components. So ftx plus fgx plus fqqx is equal to max. And you notice the process I'm going through is exactly the same as the process I went through before. The idea is to make Newton's second law problems into sort of an algorithm where you do the same thing every time. And the reason for that is because basically everything above this line is what we would call the physics. So you might hear it said that physics is simple, and that's because the law is a very simple thing. Now, to get an answer out of it, you have to do a bunch of math. So what comes below here is math. It's the math of vector equations and a little bit of algebra, maybe some trigonometry. But it's math, it's not physics. So you don't want to get those two things confused. You want to do all the physics up front by drawing a really nice free body diagram, writing out Newton's second law as a vector equation, and then just using the logic of math to do the rest of it. And math really can be an algorithm in that sense. So I write out the same thing as I did before, where I have the x component equation. Now I want to find each of these components by putting the vectors on the coordinate system. So let's do that. So ftx, I take my ft vector, I place it here on the coordinate system, and I'm going to need an angle there, but I was given an angle, so we know that this angle is 5 degrees, but that means that this angle is also theta, it's also 5 degrees, so I can draw that angle here. And to find the x component, I project down to the x-axis, and this is ftx. So you can see that this is going to be the opposite side of the triangle that I'm looking for, but the number ftx is on the negative x-axis, so my ftx value should be minus magnitude ft sine of theta. Now fgx, well, fg points down the negative y-axis as I've defined it, and you can see that if you project back, you land at 0 for the x value. So fgx is 0, and then fqq, it points along the positive x-axis, fqq, and therefore its x component is this positive number, fqqx, and that number is exactly equal to the magnitude of the vector. So I write it as plus magnitude fqq. Then we look at the right-hand side of the equation. Well, we told ourselves that the acceleration was 0, so both components of the acceleration are 0, so we just get that. And then our boxed equation we could write as fqq is equal to ft sine of theta. And we're done with that component. So what do we do next? We move on and we look at the y component. So again, we write out fty plus fgy plus fqqy is equal to may. Then we get those components. So we can see here that fty is this number here. That's the adjacent side of this triangle, and it's a positive number, so it's going to be ft cosine theta. Fgy is this number right here. Let me draw that. So it's important to remember that components of vectors are actually tick marks on the axis. It's a number there. And that's important because you want to show yourself that that's a negative number. So that's a negative number there. So I write it as minus the magnitude of fg, because this negative number here is exactly minus the length of the vector. And then finally fqq, well, fqq only points on the x-axis, so it has 0 y component, and again we have 0 for the ay. So our second boxed equation is fg is equal to ft cosine of theta. So you notice I haven't thought about the problem or the question that was asked in a very long time. And that's the point of this Newton's second law algorithm, is that you can go through and do the problem, get as much information as possible out of the problem without actually trying to answer the question. And that's exactly the way that you should do it. Now I have the tools that I need to solve any question that I want. So the question that was asked was, what is the magnitude of the charge on one ball? So that means what is absolute value of Q? So where does that appear in my boxed equations? Well, it appears within the Coulomb force, as we said before. So now we can do that step where we plug in some of the expressions of the forces. So FQQ, remember, we know the expression for the magnitude. We were given it on the first page. So I'm going to write that as K Q1 Q2 over R12 squared is equal to, I'm just going to write ft as t times sine of theta. For this particular problem, Q1 and Q2 were exactly the same, and I can just write that then as Q squared. So I have KQ squared. And the distance, R12, I don't know yet, but I can probably find it. So let's look and see. So we have a distance here, and I think we probably needed to have a length of the string, which I left out. So let's just assume that that's 1 meter here. And we'll see if we need that or not. I could write that distance, sorry, so this is L, this is theta, and instead of calling, that's definitely not the distance that we're talking about. The distance we're talking about is this distance, which is R12. So this number here, this side here, is d over 2. So I could relate these two by saying that sine of theta is equal to d over 2 over L, which tells me that d is equal to, what, 2L sine of theta. So I have an expression for d if I need it. For now, let's just write that R12 squared is equal to d squared, and we'll see if we need it. Well, in order to find out what Q is, I need to know what everything else in this equation is. So it looks like I will need that expression for L to get D, but I also don't know what T is. But of course I have a second equation from Newton's second law, and so that second equation tells me that T is equal to Fg, which I can write as mg, over cosine theta. So if I continue on with this equation, then I can write K Q squared over d squared is equal to the tension, which is now written as mg over cosine theta times sine of theta. And finally I can solve for Q. So Q then is going to be equal to mgd, mgd squared over k times sine theta over cosine theta is tangent theta. And then this was q squared, so I'll just put a square root around that there. I'm not going to plug in the numbers. I'm sorry, I should have had a number there for L to begin with, but from here you can actually calculate the numbers. So that completes